Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And this is part 10 of 10 of a little mini series within that playlist called Split Plot Designs. We're going to do an R illustration of the previous 9 videos in this little mini series. We're going to look at data from Montgomery. It's a book by Montgomery. It's table 14.7, and it's a paper manufacturer, and they're wanting to examine the tensile strength, how much energy or strength does it take to tear the paper. They're looking at 3 different pulp prep methods and 4 different cook times. And the way that this is, they have to do a big batch. They randomly pick one of the 3 pulp prep methods, and then they divide it into 4 and randomly assign a cook time to one of those. And then they repeat that. They randomly pick one of the remaining 2 pulp prep methods, split that into 4, and then randomly assign cook times to each, and they do that for the last pulp prep method. And that's as much material as they can produce on a given day. So the next day, they repeat this whole process. And so they're going to treat block or batch on a given day as the block. But notice that there's 2 randomizations. There's 2 restrictions. So they randomly pick a pulp prep method, prepare it, and then once that's done, then they divide it in 4 and randomly assign a cook time. So there's 2 randomizations here. There's a whole plot and a split plot. And so this is a nice example of a split plot design. So let's go through this. Let's enter the data, and I've entered in what's called Montgomery. And so the tensile strength is Y. That's our dependent variable. We have block. Method is the pulp prep method. And of course, temp is the temperature. Part 1 was model development. We just overall discussed the design and the methods. And here, this is the R command to do. And what's new is this air block. And so that helps us create the air for the whole plot. And so if we look at this, we're going to have method and block and the interaction for method and block. But the air structure is within block and method, so it creates this larger, this is the block method air. And then within this, they re-randomize, they separate it and re-randomize. That's why it's called within. This is within each of those. Here we use block as a factor. If we didn't, then these 2 here would get combined. So that's what, 113.8. So in this one, we do the same, but I don't use the interaction term. And notice that those 2 got summed into this 1. That's residuals. And now it's not over parameterized, and we can use that for the F test and p-values and etc. And we'll go through each of these in turn. Now, we want to create, in part 2, we looked at the design matrices. And so I want to order this by method, block, and temp, because that's the way we discussed it in the videos, the previous 9 videos. There's 3 treatments, 3 replications, or in this case, 3 blocks. M is the number levels in the second factor. And there's 4. 3 pulp methods, 4 cook times, 3 replications, or 3 blocks. So here we're just creating sort of shells of the design matrix. And now we're going to not replicate, but create the 1s and 0s necessary for the design matrix. And here's the design matrix. Oh, let me widen that out and reprint it. And so this first column is a column of 1s. The next 3 columns are the treatments. Notice it's, if you go back and watch the videos, it'll make more sense. So this is block. So there's 1, 2, 3 blocks within each factor, and then it just repeats 1, 2, 3, etc. And the next 4 columns deal with the second factor, which is temperature. And so there's 1, 2, 3, 4, and then it repeats 1, 2, 3, 4, 1, 2, 3, 4. And then the last columns, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 columns, 3 times 4, deal with the interaction. So, and then For more details, you can watch the part 2 of this series. So here we're going to create the perpendicular projection matrices for each of those little column spaces. And I need the library mask to do the generalized inverse function. So here ID is going to be the identity matrix, J is column space. It's the perpendicular projection matrix on the column space of 1. So notice we go 1 transpose, 1 inverse, 1 transpose. And that's the common theme. So the column space associated with treatments or the pulp prep methods, we go XT, XT transpose, XT inverse, XT transpose. So it's the same structure for each of these little column spaces. And for M is a perpendicular projection matrix on the whole column space, and we stored that as XTRM, which that stands for there's treatment effect, rep effect, and that M was the second factor effect. And we just go X transpose X, generalized inverse, because it's the whole matrix, it's not invertible, and then X transpose. And did I put it in? Yeah. So in here, in part 3, we looked at some properties and showed that like when we multiply the perpendicular projection matrix onto the interaction space of treatment and replication times the perpendicular projection matrix onto the interaction space between treatment and the first and second factor, so alpha and gamma, if you go back to the videos, it equals what's common. Notice there's a T common, and so it ends up being that's the common space. Anyway, these are 4 properties that we kind of used at the end of the video, showing that when you do multiply these out, it does equal what we say. Then also the mean vector structure. So the perpendicular projection matrix pre-multiply, y pre-multiplied by that perpendicular projection matrix creates a certain structure. So if we look at the mean between, for the methods, pulp prep methods, and then this is the perpendicular projection matrix onto that column space, it creates a certain structure. Notice that the means are the same, and then they're repeated a certain number of times, and they're repeated based upon the structure of this perpendicular projection matrix. And so what these mean vectors do, and I'm kind of going fast, but I'll put the program in the comment section so you can copy and paste it. And I would so encourage you to go through the previous videos and then run this R program side by side. And so these mean vectors have a specific structure, and so I'm just going to go through them fast because I think otherwise this video will get too long. So now the column spaces of this design matrix, this first command shows you that when we kind of cheated, or not cheated, but sidestepped a certain criteria and said, hey, if you take this, you just substitute the perpendicular projection matrix into the X matrix, the column space matrix, it's really essentially the same. And this property is showing you that it is. And so we take it, it's actually this, and then so it's identity minus M. In the video, we called it alpha beta, and then times alpha or X gamma. And then if we call this matrix Z, so this is Z transpose Z, generalized inverse Z transpose. That's what this ends up being. That's how you create that perpendicular projection matrix onto this column space. But we just put the perpendicular projection matrix onto the second factor, gamma, in here, and said that it'll produce the same thing, which is this, and it does. So that's a sort of a longer explanation than I really wanted to give to it. We also said that the perpendicular projection matrix on the column space of X can be broken down into the sum and differences of these perpendicular projection matrix, and this is showing you that indeed it is true that these do equal. And here, these next 3 commands are showing that these column spaces, or these perpendicular projection matrices, create orthogonal column space. So the product of those should be 0, and that's what these are these three commands are doing, showing that they are indeed 0. Now partitioning, in part 6, we looked at partitioning the total sums of squares, and this is the split plot randomized complete block design. And so this is how we would enter the command into R. And then I'm going to show you that those crazy matrix multiplications and additions create exactly what R does. So the sums of squares would be Y transpose times M. In the video was M alpha minus J. That's the sum of squares for the first factor. And so let's do it. And then the degrees of freedom is the rank of that perpendicular projection matrix. So this is what we're creating. So here, this is for method. Look at this, 2 and 128, 2 and 128. So it's exactly the same. And we're going to go through each of these. So this one, if you look at this, it's 2 and 75, 77.5. And it's this crazy matrix multiplication is exactly what R is producing. So here's the sum of squares for whole plot, 3627, rounded, of course, and 4 degrees of freedom. So it's the same. And then now let's look at the split plots. And so this is the temperature sum of squares, 3 degrees of freedom, same. This is the interaction between those, 75.2 and 6. This is a sum of squares for split plot. It's 18 and 71.5. And the sums of squares total, if we were to add each of these totals, it's 822 with 35 degrees of freedom. Now let's look at it, and if we just did the SPCRD, so we did a completely randomized design initially instead of the complete randomized complete block design. So we're leaving out the block effect in here, and so we're missing that. So they'll be combined. So it's Y transpose M alpha in the previous videos minus J. We get the same thing. Yep. Oh, I didn't do degrees of freedom. And I'm not going to go into much detail, but to show you that these crazy matrix multiplications are exactly what is produced in R. If we were to take the rank of this perpendicular projection matrix, that it would equal the degrees of freedom associated with that. So then we have the sum of squares associated with temperature. The interaction between method and temperature is 75.2. The the sums of squared air is 71.5. If you were to take the rank of this perpendicular projection matrix, it would say 18. And notice this one is interesting. So if we add up these sums of squares total, these sums of squares to get the sum of squares total, notice that it's the same as what we got in the first place. The total sum of squares is the total sum of squares. It's just how you divide it up. And I thought we should probably do, in Montgomery, they look at what I'm going to call the split plot full model. That means they use every every interaction, single term, interaction term, third order terms. And so when we look at this, there's no room for error terms because it's over parameterized, but we can still produce the sums of squares that they generate using these matrix multiplications. And so the block sum of squares, 76, which is this. This is the interaction method and block is 36.28. And to me, this is just so mind-boggling cool. So there's the method by temperature sums of squares, and then if we look at the temperature by block, it's 20.7, and we derive these perpendicular projection matrices in the videos. And so here is the three-way interaction term, method, temp, and block is 50.8. And see, to me, that's just so cool. And so again, the totals, if we were to add these sums of squares, they would equal 822. It's the same. And now for these, the SPCRD and the P full. I'm going to be done with it. But we're going to go back to the split plot randomized complete block design. Oh, I guess I don't do the F test until later. So I'm going to kind of skip this. In part 7, we looked at the sum of squares, expected sum of squares for these quadratic forms, or these, and in there I said a lot of these are 0. So if you take this perpendicular projection matrix onto that first column space of 1s, it should be 0. And this is really just showing you that indeed you do get 0 in R. And there's and we use more of a theoretical reason in part 7 of this video, but these are really showing you that when I say you take this perpendicular projection matrix, times this column space, you should get 0. And really this is all those things that we did in this video, expected sums of squares. It's showing you that when you do take that product, you do get 0. And I'll have to point you to that video. I don't want this to be too long. So now in the SPCRD design, so this is SPRCB, randomized complete block design. Now, once you produce the sums of squares, the rest, and degrees of freedom, the rest of the table is kind of just silly, because the mean squared is the sum of squares divided by its degrees of freedom in the same way. And then the F is the ratio of the mean squared divided by the mean squared residual. And you get the F values. And then the F value, with the numerator and denominator degrees of freedom, you can calculate the P value. So this is what this is saying. So if we take the sums of squares whole plot, the sum of squares error whole plot divided by its degree of freedom, you get the mean squared value, which is 9.7. So that's what's down here. And then we just go through and we save these values previously, so we're just reusing them. So here's the mean squared for treatment, for method. Here's the F value, and here's the P value. So we just reproduce that, and it's the same. So here is the mean squared for block, p-value associated with it. Here's the sum of squared error for split plot, which is this. And then we produce the mean squared for a little brain cramp there. So there's a mean squared for treatment. That scientific notation kind of threw me off there for a second. And then here's for that interaction space. We get 12, 53, and 3 and 2. So all of this matches exactly what R produces. All right. Again, I kind of went fast. I'll put the code in the comments so you can copy and paste it, and then re-watch parts 1 through 9 to verify that this indeed all makes sense. Well, I hope you enjoyed this playlist, this mini series. It's I almost have 100 videos in this playlist. I'm ready to move on, but I really enjoyed it. Hope you did. Please like the video, subscribe so you don't miss the next one, and thank you.